Okay. So in the last session on Friday, um, we had mentioned how to draw the schematics for n input NAND gate and n input NOR gate by telling that if we simply connect n PMOSes in parallel and n NMOSes in series, it will become n input NAND gate, and vice versa. Not vice versa. Similarly, if we connect n PMOSes in series and n NMOSes in parallel, it becomes a CMOS NOR gate. Then we defined what are simple gates and what are compound gates. And then we took two design problems such that in the transistor level schematic, we had both series and parallel connection between PMOSes in the pull-up network. And we had similarly parallel and series connection between NMOSes in pull-down network. And in the second example also, we had a similar kind of a design wherein we had both parallel and series. So we had a set of parallel PMOSes in series with another set of parallel, PMOSes in the pull-up, and in pull-down, similarly, we had a set of two NMOSes in series in parallel with another pair of NMOSes in series. And last, we actually tried to uh, make the transistor level schematic for a 2-input AND gate, and we told that according to the rules frame for CMOS logic design using MOSFETs, because the expression for both AND and OR gate does not have a bar over the Boolean expression, that is why we have to start considering Y bar, and because Y bar is implemented a pull down network, ultimately the logic design for AND gate involves implementing Y bar through pull down network, and then we saw that we needed a total of 1, 2, 3, 4, 5, 7, 8. So basically the conventional approach for implementing 2-input AND gate and 2-input OR gate involved 8 MOSFETs, but then when we use alternate approach, that AND or an OR gate is nothing but a cascading between a NAND and a NOT gate, or a NOR gate and a NOT gate, we found that we were able to save two transistors, in the sense the transistor count went down by 2 against 8. That is where we stopped. And now in today's discussion, we are going to take two interesting topics. So just flash to our syllabus. And today we plan to do this thing. So in the unit number 4, till now we have covered these things. So I'm going to cover today technology scaling, and also transmission gate logic, which is very important. So let us understand the meaning of this word technology scaling. So basically in the field of IC design, uh, which basically deals with designing the logic which has to be put inside the integrated circuits, and then these circuits which are designed on paper and their functionality is simulated using various backend tools. Then the verified design is then actually fabricated. So when we speak about the field of VLSI, that means it is nothing but the art of putting as many transistors in as a small silicon wafer area as possible. That means as and when the years have gone by, like in the year 1971, Ted Hoff launched the world's first 4-bit microprocessor from Intel, that is 4004. So it had only a few thousand transistors. And in that time, the smallest transistor which was fabricated on the silicon wafer was having a channel length as large as almost 1500 nanometer, that is 1.5 micrometers. So from about 1500 nanometers in 1971 to 2020, that is in a span of 49 years. In a span of 49 years, the transistors have become smaller and smaller, and they have been scaled down from a value of 1000 nanometers to almost 5 nanometers today. So the transistors have been scaled down almost by a factor of 300. So because transistors have been continuously reduced in size, that is scaled down, that is why it was possible to fabricate more and more transistors on the silicon wafer. So if you see the technology news, then Apple is planning to design its latest bionic chip A15. So even Apple's bionic chip A14 contains more than 8.3 billion transistors. So that is the level of integration of fabrication which is going on in the fabrication labs today. So the entire evolution of functionality, right from desktop PCs till smartphones, everything is a result of technology scaling. So it is not necessary for me to tell that when we use the word technology scaling, it actually means scaling down, scaling down. So while frequencies have to be scaled up, while frequencies have to be scaled up, power dissipation has to be scaled down, and also the area of the chip has to be scaled down. So we always tell that there are three design metrics in VLSI design: SAP, speed, area, and power. So speed or operating frequency has to be scaled up. Area has to be scaled down, and power also has to be scaled down. So both power dissipation should be scaled down, power consumption from the battery should also be scaled down. So when we say technology scaling, it is nothing but reducing the geometric dimensions of the MOSFET. So we do not speak about BJT at all, because BJT device is actually a misfit in the field of VLSI. Only in critical applications where a BJT will surely outperform a MOSFET, we are going to use BJTs, and that too in a very rare logic family called as BiCMOS logic family. So BiCMOS is a specialized logic family which actually combines the functionalities, that is the merits of both bipolar family and CMOS family. Okay, otherwise not. So technology scaling basically means reducing the dimensions of a transistor. Okay, so it basically means scaling down a MOSFET. And when I say scaling down, it actually means reducing and because when you reduce the dimensions of a MOSFET, then its energy requirements also go down. Like, you know, if we say logically or ideally, if you have a 100 kg man, then he may need, you know, 4 kgs of, not 4 kgs, if there is a 100 kg man, then he may need to eat about 1 kg of rice every day. But suppose if he goes to a program of dieting and he reduces from 100 kg to 70 kgs, naturally it is expected that his rice consumption should go below 1 kg. Same thing happens. So if a particular sized MOSFET, it needs 3.3 volts to operate, then when you scale down the MOSFET, when you reduce the geometries of the MOSFET, it is expected to operate at bias voltages lesser than 3.3. That is why if we see the technology roadmap, when transistors were as big as 500 nanometer, they needed 5 volts. When they came down to 350 nanometer, they needed 3.3 volts. Then 250 nanometer 2.5 volts, 180 nanometer 1.8 volts, 120 nanometer 1.2 volts, and anything below 120, 90, 65 needed only about 1 volt, and now it is even less than 1. So as the MOSFET dimensions have been scaled down, the bias voltages have also scaled down. Okay, like that. So reducing geometric dimensions of MOSFET is first understanding of scaling down, and also it means reducing the bias voltage VDD. Okay, so scaling down a MOSFET means reducing the geometric dimensions of MOSFET and also reducing the bias voltage of MOSFET. There are some exceptions to this. Okay, and when you say scaling down means we have to define that scaling, or we can say the amount of scaling is expressed in terms of a factor S called as scaling factor. Okay, and important thing is that the scaling factor is always greater than 1. Okay, it's always greater than 1. Okay, now when we speak about geometric dimensions, we know that in the 3D planar structure of a MOSFET, which we had discussed, I think so, in which lecture I have to see. Yeah, so here we can see that there are basically 4 parameters of a MOSFET which define geometry. So we have in the 3D planar structure, we have the width W, we have the channel length L, which is nothing but the drain to source separation. We have the oxide thickness Tox, and we have the junction depth Xj. So width W, channel length L, oxide thickness Tox, and junction depth Xj are called as the geometries of the MOSFET, while VDS, VGS, and VDD are called as the electrical parameters of the MOSFET. So coming back, when I say geometric dimensions, I actually mean width W, channel length L, Tox, and Xj. Okay, yeah. Scaling factor. So if my new width is W dash, then it will be equal to W upon S. New length L dash is L upon S. New oxide thickness is Tox dash equal to Tox upon S. So we see that because S is greater than 1, if I keep S equal to 2, then my new width will be half of original, new length will be half of original, and oxide thickness will also be half of original. That is why we say that the amount of scaling is expressed in terms of a factor called as scaling factor, denoted as S, and S is always greater than 1. Now basically the interest of the discussion today is that if I scale down the MOSFET's geometric parameters, what benefit I achieve in the three design metrics, that is power, speed and area. So there is a purpose or there is some meaning in technology scaling. If after scaling down a MOSFET by a factor S, and where S is greater than 1, if my area reduces, if my frequency increases and my power dissipation also reduces, only then there is a meaning in doing technology scaling. So we are going to justify today, is it worth scaling down a MOSFET? So now we have to classify that what are the different ways that I can scale down a transistor. Okay, so that is why we have to classify what is called as transistor scaling. Okay, so transistor scaling, you can also see it as MOSFET scaling. So transistor scaling is basically classified into two. One is called as, not transistor scaling, it is actually like this. It's scaling only, it's plain scaling. First is called as transistor scaling and second is called as interconnect scaling. So in unit number 2, we have defined what are interconnects. So interconnects are nothing but they are connecting mediums, and anything called can be called as an interconnect. So passivation layer, N plus, P plus, wires, vias, everything can be called as an interconnect, right? So there are two aspects of a silicon wafer. One is the transistors or the active devices, and second thing is that the elements which connect the transistors together. That is why interconnect actually forms more than 70% of the area on a silicon wafer, and only remaining 30% is actually taken by the transistors. So that is why once we have reached the saturation of transistor scaling, then in order to further reduce the area of the chip, we have to resort to the second aspect of an integrated circuit, that is interconnect scaling. So transistor scaling has almost reached its saturation at 5 nanometers. So now they are focusing on reducing the area by finding ways and means how they can actually scale down the interconnects. Okay, so transistor scaling is further classified as, first is called as constant field scaling, second is called as constant voltage scaling, and third is called as lateral scaling, also known as gate shrink. Okay, so from the name itself we can come to know that what should be the meaning of constant field scaling and constant voltage scaling. So all of us know that the electric field E is voltage upon distance. Okay, so when we scale down a MOSFET in such a way that all the electric fields which are present inside the MOSFET structure remain constant, it is called as constant field. On the other hand, if we do not care if the electric field does not remain constant, but only the voltage remains constant, it is called as constant voltage scaling. And third time, when we say lateral scaling or gate shrink, we are going to only scale down the oxide thickness Tox. So we already told before that a MOSFET structure has two fields. One is the lateral electric field, which is equal to you know um, VDD upon L, and we have the vertical electric field which is equal to VGS upon Tx. So it is very clear that if I want to keep the lateral field constant, now we already know that technology scaling means scaling down the geometry of MOSFET. So as I told you that if I want to scale down a MOSFET, I have to reduce the width by a factor S. I have to reduce length by a factor S, and also the TOX by a factor S. So it's very natural that if I reduce the value of L by S, then if I only scale down L and do not scale down VDD, then my electric field is going to get multiplied by S. So electric field will increase. So it does not become an example of constant field. Similarly, here also the vertical electric field is VGS upon TOX. So if I only scale down TOX, so if I say if I scale down the length L by S, then my new field will be VDD upon L into S. Similarly, if I scale down the oxide thickness by a factor S, then my new field will be VGS upon TOX into S. And because S is greater than 1, my field will not remain constant. That is why in constant field scaling, I make sure that my E lat and E ver remain constant. That means what? I have to also scale down VDD by S and VGS by S. In that case, my field will remain constant. Okay, so understand this thing that constant field scaling is a kind of scaling wherein I ensure that all the electric fields which are present inside a MOSFET, they remain constant. That is why in constant field scaling, the parameters which I am going to scale down are as follows. So I am going to scale down width, length and TOX as well as my supply voltage VDD. So when VDD scales down, automatically VGS is also going to scale down. Okay. In constant voltage scaling, I will make sure that my supply voltage is constant. That is why here the electric fields will not remain constant. So in constant voltage scaling, what I do is that I scale down W, L and TOX, but my VDD remains constant. So it is not scaled down. Okay, in another words, I can say in constant field scaling, I will scale down width, scale down length, scale down TOX and also scale down the supply voltage. In here, I am going to scale down width, scale down length, scale down oxide thickness, but I am not going to scale down VDD. That means VDD will remain VDD in constant voltage scaling, but in constant field scaling, VDD is also scaled down. Lateral shrink, what I do is that I am only going to change the oxide thickness. So in this case, my width will remain as before, length will remain as before, and only my TOX is going to be scaled down. That is what is called as gate shrink. Okay, and VDD will also be scaled down. Okay, these are three different ways in which transistors are scaled, and let me tell you that this constant field scaling is found to be the best because it is that scaling in which we get enhancement in all three design parameters, that is speed increases, area reduces and power dissipation reduces. But in other two kinds of scaling, constant voltage and lateral scaling, sometimes we get reduction in power dissipation, but the area increases. Sometimes area reduces, power dissipation reduces, but the operating frequency actually reduces. So it is uh, that is why constant field scaling is said to be the best because it gives us enhancement in all three design metrics, that is speed, area and power. Okay. Interconnect scaling is not in syllabus, so I'm not going to discuss it, but it does exist. Okay. So So Fmax should increase, area should reduce, and power dissipation should reduce. So I can say that okay. So that scaling technique is best, which offers us the result shown. That is, it gives us a scale up in Fmax, a scale down in area, and also a scale down in power dissipation. So this constant field scaling is also known as Dennard scaling. There was a scientist called as Dennard who actually devised this particular method. That is why constant field somebody asked, yes, Dennard scaling is nothing but constant field scaling. Okay, so Dennard scaling is nothing but constant field scaling. Now we are going to mathematically derive whether this Dennard scaling offers us an increase in speed, reduction in area, and reduction in power dissipation. So this is the analytical part of the topic. So what I do is that I first write down the parameter here. We have two tables. Width, length, oxide thickness. Last is then it is we have VDD. Then we have substrate doping concentration Na. Okay, and here we are going to write down the type of scaling. Okay, so scaling method. This is constant field, constant voltage, and we have lateral scaling already defined. So in constant field scaling, we can say the new value will be, okay, new values will be here. So we can say W dash, L dash, Tox dash, VDD dash, and NA dash. Okay, so we can either write down W by AC or we can simply say 1 by S. Okay, so if there is no confusion, then no problem. Constant field scaling, W by S, L by S, Tox by S, and VDD dash is VDD by S, and this is actually into S. Okay, constant voltage scaling, W by S, L by S, Tox by S, no scaling in VDD, and here again lateral scaling, only Tox is scaled down, so new value is same as old, L, Tox by S, VDD by S, and this is equal to NA. Okay, so fine. Second table which we make is to actually compute. So we are going to fill the table after doing some kind of computations, not now. So in the next table, what I write is the performance parameter. Okay. So we can actually write down scaled parameters here. Here we have a column called as sensitivity. Sensitivity is nothing but the mathematical formula, nothing else. And third, we write down the parameter which is obtained. And we can write down so performance parameter, sensitivity, and parameter after constant field scaling. So we can say this is the old parameter, this is the new parameter after scaling, and this is the sensitivity. Fine. So the first parameter is beta, or it is also called as gain factor. So I'll be teaching you this thing, but for the sake of discussion, we are just putting down. First is the gain factor beta. Second is the device current, that is the current carrying ability of the MOSFET. Third parameter is the resistance R. It is also called as on-state resistance of the device. So we can say R or R on. Fourth is the gate capacitance CG. The fifth parameter is the time constant, which is nothing but R on into CG. The sixth parameter is the operating frequency F, which is equal to a reciprocal of the time constant. Seventh is actually area. So area of MOSFET is always equal to width into length. And eighth parameter is power dissipation, which is equal to Cg into, okay fine, anyways, what we were supposed to write down in the next column, I wrote it here, no problem. Tau, F, A and P. So beta is equal to mu epsilon ox upon T ox into W by L. Okay, IDS is equal to beta into VGS minus threshold voltage whole square. R on is nothing but equal to VDD on IDS. Gate capacitance is it is basically equal to epsilon A over D. So it is epsilon ox into area is width into length upon T ox. Tau is R on into Cg. F is 1 over tau. Area is W into L. And my power dissipation is equal to Cg into VDD square into F. The third column we are going to fill after doing some calculations. Okay, so first parameter is beta. See how I do it. So beta is equal to mu n, that is a mobility of electron, into epsilon ox upon T ox into W by L, right? So beta dash is equal to mu n dash into epsilon ox dash upon T ox dash into W dash by L dash. Now we should know here that W dash is W by S, L dash is L by S. Similarly, T ox dash is T ox upon S, because we are considering constant field scaling. Here mu n dash is equal to mu n because we know that the mobility of electrons is not changed by scaling, right? Because mobility of electron is a function of temperature. If we know the electron mobility is a function of temperature, not the dimensions of the MOSFET. So we can put these values here. So beta dash will now be equal to mu n, and then yeah, also epsilon ox is also same. So epsilon ox is basically equal to epsilon 0 into epsilon r, which is equal to absolute permittivity into epsilon of SiO2, which happens to be 3.9. So we can basically say that epsilon ox dash is also equal to epsilon ox. So epsilon ox and mu n will not change. So it is mu n into epsilon ox upon T ox by S into W by S upon L by S. So when we rearrange the terms, what we get is this. We get mu n into epsilon ox upon T ox into W by L into what it will be? Yes?
So it will be S.
S or 1 upon S?
S होगा ना सर?
S.
S होगा बराबर ना? Yes. So my new value of beta dash will now be equal to beta into S. So the gain factor has increased. Gain factor has increased. So this is good actually. That means what? We are getting a larger gain. So the new value of beta will be beta into S. Okay, and please understand one thing. S is greater than 1. Now we go to IDS. So second parameter IDS is told it is equal to beta into VGS minus VT whole square. So IDS dash is equal to beta dash into VGS dash minus VT dash whole square. Okay, so we know that our beta dash is actually beta into S, and this will nothing but be equal to 1 over S square. So it becomes beta upon S. So basically my new value of current is now is equal to IDS upon S, which is actually good because the current has been scaled down. So the current has been scaled down. So we can also write down that the new value is IDS upon S. Okay, R on third parameter. R on is VDD upon IDS. So we can say R on dash is VDD dash upon IDS dash, which is equal to VDD over S, because we are scaling down the voltage also. IDS upon S equal to VDD upon IDS. So basically R on dash continues to remain equal to R on. There is no effect of scaling factor on the resistance. Okay, only if it would have been scaled down, it would be an added advantage. Anyways, so there is no change. So it is equal to R on. Now we come to CG, that is a gate capacitance. Gate capacitance is epsilon A by D. So it is epsilon ox into area upon distance. So Cg dash is equal to epsilon ox dash into W dash into L dash upon T ox dash. Epsilon ox dash is equal to epsilon ox. We have W by S into L by S upon T ox by S. It comes out to be epsilon ox into WL upon T ox into 1 over S. Basically, it is Cg upon S. So the gate capacitance has reduced because S is greater than 1. That is why Cg upon S indicates a reduction in gate capacitance, which is very good because it will actually enhance the operating frequency. So now, conclusion of fourth point is that it is Cg over S. So when we scale down a MOSFET, the gate capacitance reduces. Let us go to fifth parameter, that is time constant. So tau is equal to R on into Cg. So tau dash is equal to R on dash into Cg dash. Now we know that R on has remained R on while Cg dash has become Cg over S. So now it becomes equal to tau over S. Okay. So the new value is, so time constant has reduced by the scaling factor. It is going to enhance the operating frequency. Sixth parameter is f equal to 1 over tau. So f dash is equal to 1 over tau dash is equal to 1 over tau by s, which is equal to s into 1 by tau is equal to s into f. So if you see here, so the operating frequency, the new operating frequency is now multiplied by the old operating frequency by a factor of s. So my conclusion is it is f into s. Area area is width into length. So a dash is w dash into l dash is equal to w by s into l by s, which is equal to wl upon s square, which is equal to a by s square. The conclusion is power dissipation so p dash is cg dash into vdd dash whole square into f dash. We know that cg dash is cg by s, vdd already we are scaling down square, and we have got an enhancement in the frequency s into f. So now it becomes cg into vdd square into f into 1 over s square, which is equal to old power divided by s square. So we have p over s square. Okay. Now we are in position to analyze if constant field scaling or Dennard scaling is going to help us. Okay. So let us assume that if the scaling factor is equal to root 2. Okay, so the new values will be root 2 into beta we see here in the area and power aspects, we are getting a square law benefit by scaling down a transistor. Okay, so we see here that frequency is multiplied by a number greater than 1, area is getting divided by a number greater than 1, and power dissipation also is getting divided by a factor greater than 1. That means what? We can say this is good. Okay, so in the speed we can say it is good. In area also it is good. Power also it is good. Okay, that means I am getting the benefits in speed, area and power if I resort to constant field scaling. So student can take it as home practice, that what will be the value of new parameters beta, IDS, Ron, CG, tau, F, A and P for other two types of scaling, that is constant voltage scaling and lateral scaling, and you'll surely see that the remaining two scaling methods will not give you enhancements in all three parameters, that is speed, area and power. That is why we say that constant field scaling or Dennard scaling is the best choice if you want to scale down a transistor, because this method gives you enhancement in all three performance parameters of a MOSFET. Okay, so here we can write a comment. We are seeing here that as the channel length has reduced, as the channel length has reduced, the supply voltages also have reduced. So when I say here VDD, actually it is a core voltage.